Alright, SPH3U. This is video number 5, and we're starting off with yet another little experiment. This is a clip from YouTube from ABC. It's burning foods to measure calories, and if you want to see the whole thing, it's going to be in the description underneath the timestamps. I would suggest it. But basically, I've got it muted right now, so we're going to get this out of the way. Actually, first, we're going to talk about calorimetry today, and calorimetry is a way to measure calories by, heat transfer. And one of the calorimeters we're going to learn about actually does burn stuff to measure the calories. So you're going to see that here. What's going on here is he's going to add liquid oxygen to these oats. These are toasted oats.
Get it and hold it there. All right.
Did I do it too soon?
No, that was great. So now you're getting a sense of how much energy there are in those toasted oats. They're really toasted at this point, right? Very, very still going. Very, very bright flame.
Yeah.
All right, let's try it with the cheese puffs.
Okay, now do I need to hold it on there?
So toasted oats, you saw how big the flame was. We're going to do the same thing with cheese puffs. What do you guys think? Oats versus cheese puffs, which one has more calories? Well, you're about to very visually find out. Here we go.
Coming off those cheese puffs.
You can feel the heat from that.
You can feel it, you can see it. I'm going to cover some of these up here.
So just like the lady said, you can feel the heat coming off of that. And heat, right, that transfers thermal energy. So oxygen combines with food and gives energy. That's what we use to do human stuff. And we liberate energy we liberate chemical energy from our food and turn it into chemical energy inside us, and then use that chemical energy to, make YouTube videos for your physics class or something. So that's what we're talking about. We're talking about calorimetry. Now that's a simple calorimeter. This one is the fancy version of it. It's called a bomb calorimeter. A bomb calorimeter. And it uses a design where there's this thing called the bomb, which is just a sealed vessel. It's full of oxygen. The sample goes in there. There's an ignition box, so it's just like a spark. And then the pure oxygen atmosphere will burn the food, and then it gets hot, but it's stuck inside water. And so it gets hot, it releases its heat to the water. There's a little stirrer in here, and there's a thermometer. So full oxygen atmosphere, burns the food in there, gets hot, heats up the water. It's a known quantity of water. It's like maybe a liter of water or something like that. There's a stirrer. The motor is outside because as the motor works, it would heat up. So they put the motor outside so that the heat wouldn't go in. Boom, energy gets released. And you can figure out how much energy the food releases by figuring how hot the water gets. Because as we've learned now, Q equals MC delta T. There's a delta there. I'm going to pause and find a delta symbol. There, I found the delta symbol. So Q equals MC delta T. If you know the mass of the water and the specific heat capacity of the water, 4.184 joules per gram degree Celsius, and you figure out the starting temperature and the ending temperature, you figure out how much heat the water gained. And then you have kind of like Q water is negative Q of the food. And kind of like that. And that's the whole idea of a calorimeter. If you figure out how much thermal energy the water gained, that's how much thermal energy the food lost. And that's how much thermal energy will get released when your body processes that food. So that's the basic design of a calorimeter. It's just a known quantity of water that has a known starting temperature, and then the final temperature tells you how much heat was released by the sample. And that's the first part here, right? That's the design and use of calorimeters. They are designed to trap heat by water and figure out how hot the water gets, and they used to to figure out the calorie content of foods. Yeah. So let's jump into solving a calorimetry problem. Solving a calorimeter problem. And all I'm going to do here for the keep in mind is take away the water is very good at absorbing heat, because we're still keeping the same heat lost by one object must be gained by the other, and we'll just change the current topic to solving a calorimetry problem. Solving a calorimetry problem. Take that away, and let's jump on forwards. This is to support your calorimetry lab. We'll go over this when we talk more about that lab. There'll be a different video. So here's a problem. Here's a problem for us to do. And I'm going to pause the video and set up the whole whiteboard thing. So just a sec. Oop. And we're set up. So we're going to solve this problem. This was actually a test problem, a couple of years ago. We have a metal block. It's at 100 degrees Celsius, and it's dumped into a calorimeter. And it's in water. And the water is at 32.8 degrees Celsius. It starts at 32.8 degrees Celsius, and there's 120 grams of it. Grams of water. And the block was also 24.2 grams to start. Right, 24.2 grams of block. And the first question goes, why the block reduced in temperature by almost 70 while the water only increased by about 2 degrees? And what that's referring to is the final temperature. The final temperature, both the 100 degrees and the 32.8 degrees ended up as a final temperature after everything was equalized. You know what, actually I'm just draw this as a separate calorimeter because that'll make more sense, right? Time after time, some amount of time, we don't know what amount of time it was. Both the block and the water are both at 34.5 degrees Celsius. 34.5 degrees Celsius. So both of them, 34.5 degrees Celsius. They have traded heat. So which way is the heat flowing? Well, it's obviously flowing out. The heat is flowing out of the metal block and into the water. Can't draw arrows apparently. There we go, heat's flowing out into the water. The question is, why so much, why did the block lose so much and the water gain so little in terms of temperature? Number one, there's more mass of H2O. Right? There's more mass of H2O, therefore harder to heat, to change temperature. Change temperature. So it's harder to change the temperature because there's just more of it. And number two, water has a high heat capacity. Compared to most metals. Compared to metal. It takes a lot of energy to heat up water compared to typical metal. Sometimes up to 10 times. Sometimes 10 times the amount of energy. So that's the first question done, part A. The second one is asking how much energy transferred from the metal block into the water. Well, we have two options here. There's the metal, right? The metal has a Q, and the water also has a Q. Has a Q. We'll make that maybe Q water and Q metal. Q metal and Q water. Both of them have the same formula, M times C times delta T. m times c times delta t. But this is for the water, so it's the mass of the water, the heat capacity of the water, and the change in temperature of the water. And this is the mass of the metal, the heat capacity of the metal, and the change in temperature of the metal. So we could figure out Q for either object. We have a formula for the Q for either object. The question becomes, what do we know? What do we know? Okay, and just to remind you that both of them ended up, we know the change in temperature of both. So I'm going to grab the green marker and we'll see what we know and what we don't. We know the mass of the metal that was given to us, right? 24.2 grams. We know the mass of the water that was given to us, 120 grams. We know the temperature change of the metal, or we can figure it out pretty easily. It's like 65.5, right? 65. It started at 100, it went to 34.5. It's minus 65.5 degrees Celsius, right? That's minus 65.5 degrees Celsius. We know the temperature change of the water, right? It went up by 1.7 degrees Celsius, so that's good. Plus 1.7 degrees Celsius. So the only thing we're missing is the heat capacity. Do we know the heat capacity of the metal? No, it's not given to us. Do we know the heat capacity of water? Yes, it is a standardized thing, kind of like the gravity on Earth. We know that that's 4.184 joules per gram degrees Celsius. So we know stuff about the water that we don't know about the metal. So we're going to use the water's heat to figure out how much heat the water gained, and that'll tell us how much heat the metal lost, because as mentioned earlier and as mentioned in the top there, right, the heat lost by one object must be gained by the other object. That's the first law of thermodynamics, that heat can only be transferred, that energy can only be transferred, it can't be destroyed. So we're using water, Q water. So Q water is M water, C water, delta T water. We know the mass of the water, it's 120 grams. We know the specific heat capacity of water because it's given to us. It's a standard quantity, 4.184 joules per gram degree Celsius. And we know the temperature change because it started at 32.8 and it ended up at 34.5. So that is plus 1.7 degrees Celsius, multiplied by 1.7 degrees Celsius. All right, so we get out a calculator, we do a little multiplication. 120 times 4.184 times 1.7. This is just this is just a formality that I've put a plus there. Please don't think that I'm adding the 1.7. I am multiplying by 1.7. And so I end up with 853 joules. So the water gained plus 853.5 joules, or approximately, because we only have two significant digits, the 120, two sig digs on the 120, the 1 and the 2, is 850 joules, approximately 850 joules plus 850, which means that that's the heat transfer. That is the heat gained by the water could only come from one place, and that's the metal. So this heat, 850 joules, left the metal and entered the water. 850 joules. So that's the first part of this, is figuring out how much energy was transferred. And then the second part, which I'm going to extend here, it says, using the answer to part B, determine the specific heat capacity of the metal. Right? That's the thing that we didn't know. We don't know the specific heat capacity of the metal. We don't know that. But having just found this 850 joules, well, actually we'll take this 853 joules, and we're going to say, that is that. Well, that heat is that heat, right? It's the same heat. Whatever the metal gave up is the heat that the water gained. So that means that the Q of the metal is known. We now know this Q. We know that because we did all this work down here. And so now we only have one thing that's unknown about this, and we can solve it. So I'm going to sneak this on over, and we're going to review what we know about this metal. We know that the heat of the metal is minus 850 joules. It lost 850 joules of energy. We know that the mass of the metal was 24.2 grams. And we know the temperature change of the metal is minus 65.5 degrees Celsius because it started at 100 and it ended up at 34.5 degrees Celsius. The C of the metal, the heat capacity of the metal, is our unknown. So Q is m times C times delta T. Q is m times C times delta T. We want to solve for C. Solve for C, that's what we're solving for. So to do that, we have to get the m and the delta T out of here. We're going to divide by m times delta T on both sides of the equation. On this side, it'll reduce to 1. On this side, it'll stick around. So Q over m times delta T is equal to C. Use m originally equals to C. And we have all of these. Q is minus 850 joules. The mass is 24.2 grams. And the delta T is minus 65.5 degrees Celsius. And that should be equal to C. C is equal to. When you're doing this, just take a quick second to see that it'll come out in joules per gram degrees Celsius. Yes, it will. Then throw it in your calculator. When you do it like this, because we're dividing by two things, I really highly suggest putting in your calculator with brackets. So I'm going to do that. I'm going to go minus 850 divided by, let's just review what we're doing there. Yeah, you can see that there. Divided by, and then I'm going to open a bracket, 24.2 times minus 65.5. All right, so that's inside brackets now. And that'll make sure that I get it right. 0.536 joules per gram degrees Celsius. I got that unit from looking at joules, grams, and degrees Celsius. But of course, with significant digits, that's actually 0.54 joules per gram degrees Celsius. That's our actual final answer. So if we looked at a heat capacity of metals, a heat capacity of different metals, we might be able to figure out which metal this is now, which is actually the last piece of this question is which metal is it? Which metal is it? I'm going to pause for a sec and find a heat capacity table of metals, and we'll compare. So I found a heat capacity table of some metals. Just as a reminder, our target is 0.54, and here's different heat capacities in different units. Ours is in joules per gram degree Celsius, but in terms of SI, that's actually the same as kilojoules per kilogram Kelvin. So if I zoom in here, right, we can actually look for 0.54 on this list. 0.46, 0.46, 0.48, 0.54, there we go. So it could be nickel. Nickel is a possibility for this metal. So that's a way that you could use calorimetry to actually solve for what kind of substance you're looking at. Let me get that out of there. And we're going to jump over to back to the screen here, and we're going to go to the next problem. Ooh, that's not great. There we go. We're going to jump to the next problem, which is finding a final temperature when two things mix. This is a little bit more complicated. So again, I'm going to jump over to the whiteboard, and we're going to solve it. So solving a mixing problem, right? A mixing problem. Let's just read the question here first. 2 cups of water having a temperature of masses, having mass of 150 grams and a mass of 250 grams, and temperatures of T1 is 30 and T2 is 75. So T1 is M1 and T2 is M2. They're mixed in an isolated system, and we want to predict the final temperature of the water. So yeah, I'm going to pause for a sec. We're going to move over to the whiteboard, and I'll see you over there. And I'm back. So once again, we're going to use the exact same formula we have before. Q equals M times C times delta T, we're mixing 2 liquids, a hot liquid and a cold liquid. So let's just look at what that kind of looks like. M1, right? M1 is 150 grams and has a temperature of 30 degrees Celsius. And M2 is 250 grams, and it has the temperature of 75.0 degrees Celsius. There's actually kind of 2 ways that you could go about this problem. There's kind of a conceptually simpler but more long method, and then there's a shortcut method. These are both water, so this is water, so that means that we know their heat capacity. It's 4.184 joules per gram degree Celsius, and it's 4.184 joules per gram degree Celsius. We actually have enough to calculate their heat. So here's the first method of solving this problem. And again, it's conceptually simpler, but it takes a little while. And that method, so method one is find how much energy each is carrying. With a baseline, right, from 0 degrees Celsius. Just like any energy term, we have to decide a baseline that we have as an energy term. You could figure out how much energy it took to heat this up from 0 degrees Celsius and how much energy it took to heat this up from 0 degrees Celsius, and then combine them into a total. So let's do that. Q1 is M1 C1 delta T1, but because we're going from 0 degrees Celsius, delta T1 is just going to be 30 degrees Celsius. So that's going to be 150 grams times 4.184 joules per gram degrees Celsius times 30 degrees Celsius, right, which is a number that I'm going to pause for because which is 18,828. So 18,828 joules. That's Q1 from 0 degrees Celsius. Q2, similar setup, except we're using the numbers for number 2, is 250 grams times 75. Oh, sorry, times same the C, right? C, the heat capacity for 2, 4.184 joules per gram degrees Celsius times 75 degrees Celsius. Right, 75 degrees Celsius. And we'll put that into our calculator. You know what? This is fast enough that I don't need to pause it for anything. 4.184 times 75 is 78,450 joules. So if we had been heating these both up from 0 degrees Celsius, this one would have needed 18,000 joules. This one would have needed 78,050 joules. And we can get a total, a Q of a total is going to be just those two added together. So I'll add my 18,828. Oh, I screwed up. Let me do that again. 18,828 plus 78,450. 97,278 joules. 97,278 joules. We have a mass for them. Just combine the two mass. The mass of the total together is going to be 400 grams, because the two of them together are 400 grams. And this only works, this method only works if they have the same heat capacity. And they do, because they're both water. 4.184 joules per gram degrees Celsius. Then we take this guy, right, now that we've got the total energy that we just got from the individual energies, the total energy from 0, and we pretend we heated up a 400 gram mass of water from 0 degrees Celsius using this much total energy, and we ask ourselves how much final temperature would it have? And that should give us the total final temperature of the two of them mixing. So because energy can't be created or destroyed, it can only change forms, it's an effective way to do things. So we have to rearrange this for delta T. Q equals mc delta T. We're looking for temperature. And once again, the thing that sets this off, that makes this work, is we're going from 0 degrees Celsius. So if we're going from 0 degrees Celsius, just like if we're starting speed at 0 meters per second or height at 0 meters, it becomes m times c times the final temperature. Then we can rearrange for this. To rearrange for this, we divide by mc on both sides. Divide by mc on both sides. That drops out, that drops out. So the final temperature is just going to be Q over m times c, which is 97,278 joules divided by the mass, the combined mass, 400 grams, times the heat capacity, 4.184 joules per gram degrees Celsius. And I'm running out of room. I'm going to give myself a bit more room here. Is equal to, and let's just do the math here. Once again, paying attention to brackets. So I'm going to take that, that's already my answer. I'm going to divide it by, open a bracket, 400 times 4.184, close the bracket so that that's below, and I get 58.125 degrees Celsius. Sig digs, I have 2 sig digs. 2 sig digs from the 250 and the 150. 250 and the 150. So I just take the 5 and the 8, so 58 degrees Celsius is my final answer. So that's one way to do it, and then we can actually do a quick little check. Does that make sense? Does 58 make sense? Well, there's more water on the 75, so it should be closer to 75 than it is to 30, and so 58 does make sense to me. That is a good final answer. So that's the first way to solve this problem. I'm going to show you the other way to solve this problem, which is faster and more beautiful and works for things that don't have the same heat capacity just as well as it does for things that do have the same heat capacity. Okay, so we're going to solve it the other way. The other way involves putting the two of them together, taking the heat that transfers over and realizing that the Q gained by this is going to be the Q lost by this, which means that Q1, which is positive, Q1, which is positive, is equal to negative Q2, because number 2 loses energy and number 1 gains energy. Which means we get to use this equation, Q equals mCT, but with the appropriate things. So that means M1 times C1 times delta T1 is equal to negative, the negative has to be there, M2 times C2 times delta T2, right? All we've done is taken that formula and put it in, including our numbers. One nice thing about this is that both of these are the same number. C1 and C2 are both the same. C1 and C2 are both the same. So, what we can do there, because they're the same numbers, they just reduce to 1 because they're on opposite sides. If you want to prove it, this divides by C1, which means this divides by C1, and then C2 over C1 drops out because they're the same. So we're left with M1 delta T1 equals M2 delta T2. Do a little negative, sorry, M2 delta T2. And what we now have to do is actually open up the delta T and actually put in the numbers that we have. You can do this without putting in the numbers, and actually as a physicist I would recommend doing it without putting in the numbers, but in this case we're gonna do it the other way because it's just easier to track stuff when you have the numbers in front of you. And I'm going to keep these numbers. So M1 is 150 grams, and delta T1, this thing's going to start at 30 degrees Celsius and get to some kind of final temperature. So there's going to be a final temperature, and we're going to take away 30 degrees Celsius to be able to figure out delta T, because we want the change in temperature. Now same logic on this side, except there's a minus here, minus M2 times, there's going to be a final temperature minus its initial temperature, which was 75 degrees. That one's going to end up negative. Right, this one's going to end up negative because it's going to lose energy, but that doesn't change this. It doesn't change these signs and where they are, because delta T is always final minus initial, just like distance is final minus initial. Now the next piece is actually to distribute this in, right? To distribute it in. Usually we like factoring in math and in physics, but in this case it's actually easier to solve this if you distribute it in. So this will be 150 grams times TF minus 30 degrees Celsius times 150 grams. Or I guess we can do it this way. Minus 150 grams times 30 degrees Celsius. And on this side, that's going to equal negative minus 250 grams minus 250 grams times TF. And then the minus is going to interact with this minus because we're distributing it in. And you're going to end up with plus 250 grams times 75 degrees Celsius. Right? Because that's how math works. What I'm doing there is I took this as one thing as I distributed it in, just to make things a little bit easier for me. So the minus counted when I multiplied it in, and that's like that. So we can't do anything to the thing that has TF because it's a variable, but we can do things to these. The first thing we can do is actually do that multiplication. 150 times 30 is 4,500 gram degrees Celsiuses. This part out here stays the same, 150 grams times TF. Over here we have negative 250 grams TF, grams times TF, plus, and 250 times 75, I don't know. So 250 times 75, 18,750. 18,750 gram degrees Celsiuses. 18,750 grams degrees Celsiuses. And now we can combine them because these are just numbers. These are just numbers. Right? They can add and subtract. So I'm going to, and these are just numbers now. They can add and subtract. So I can bring this one over and this one over there, and I end up with 400 grams final temperature equals, and so yeah, the minus 250 came over, became plus 250. All right, plus 250, plus 250. Do the same thing on both sides. 400 grams per minus 4,500, plus 4,500 would take it away on this side. And so that's plus 4,500 on this side. That's it's 50 plus 4,500, which is 23,250 grams degrees Celsius. Right, and now you have 400 TF equals 23,250, and then TF, you divide by 400 grams, divide by 400 grams, and TF is going to be 23,250 divided by 400, so TF here is going to be 23,250 divided by 400, which is 58.125 degrees Celsius, or 58 degrees Celsius, exactly what we got using the other method. Now that takes a long time to set up. That was like a 10-minute solve, but it is the only method to solve when there's two different heat capacities that you're dealing with. Well, I say the only method. There is definitely more than one way to solve it, but it's kind of tricky. I mean, this sure looks tricky, but it is possible. So that is solving for a final temperature. This is plenty of time, so I'm not going to solve for a problem with different substances. Time permits, nah, not going to do that. If you're curious about how to solve for different C's, all it's going to do is make more things to multiply by in here. So conceptually speaking, it's not that much worse. It just looks a lot worse when you put it all out on a whiteboard. So, yeah, that's it. That's calorimetry and solving mixing problems. There's a few of them in that worksheet from the last video, so try them out. And yeah, I'll see you in class.